Okay, so the key to building a power series is that we start with the Taylor polynomial, and then all we do is hit dot, dot, dot at the end. So Taylor polynomial becomes a power series if we just keep doing those derivatives forever. So at this stage, we're still just doing the polynomials. And that's the practical part. That's what our calculators and computers are using. They're using a Taylor polynomial because the Taylor polynomial is the approximation that's within the remainder of whatever your target is. So let's go ahead and do Taylor polynomial for these two functions. So they want us to go out to a polynomial with n equals 3. So remember that when n is 3, that means the third order. That's not the number of terms. The number of terms usually is one more than n because we have a constant term. So the nth order Taylor polynomial is the degree of the polynomial, not the number of terms. So the first thing we do is our sequence of derivatives. So if we start with the function that we have here, y equals tangent of x, we need to get down to the third derivative. And we just sort of do it like we're working with a spreadsheet. So the derivative of tangent is secant squared. The second derivative will be the derivative of secant squared, so we have to use a chain rule. So first thing is that that's 2 secant to the 1. We bring down the 2, we subtract 1, and then we have to multiply by the derivative of the base up here, and the base is secant of x. So we have to now multiply by secant times tangent. So if we multiply by secant times tangent, we'll end up with this as our second derivative. And we quickly see why we would not want to go beyond the third order Taylor polynomial here, because we have one more derivative, and that just seems like about as bad as we would want to get. Right, now we have to use the product rule. So here I'm thinking of this function multiplied by that function. So we'll use product rule for this derivative. So product rule is first derivative second. So we have first. And then what's the derivative of the second?
Secant squared.
Secant squared. So that's going to actually make this secant to the 4th power. Here. So first derivative second. Plus the derivative of the first times the second. Derivative of the first, we have to use the chain rule, of course. So we're going to get 4 secant to the 1. All right, so derivative of this, 4 secant to the 1, multiplied by secant, multiplied by secant's derivative, which is sectan. So we get secant squared tangent. But then we have to multiply by second, giving us a tan squared there. So that is our third derivative. Now, we next in our column, if we're thinking about this as a spreadsheet, we need to plug in the center, and that's our choice. So they're asking us to approximate the value of tangent of -0.1, -1/10. And what we would like to do is choose a center for the Taylor polynomial that we know values for, that is also close to -1/10. So we're thinking about the x-axis, and we want to pick a center that's as close as possible to -1/10 that has tangent values that we know, so that we can plug in, and secant values, because we've got to plug in and evaluate all of these. So we want to think about what is our center most likely. What do you think we should choose for the center? there's 0, there's -1/10. What are the values that we know on the unit circle? 0 we know. -π/6 we know. So if we look at our unit circle, the two values that we know trig functions of are these two values. -1/10 is going to be closer to 0. We could pick -π/6, but we want to pick, so those are the only two trig values that we know that are surrounding -1/10, right? Those are the two that we could choose from. -1/10 is closer to 0 than it is to -π/6. -π/6 is about -1/2. So we're closer to 0. So we're going to choose this as our center. So now we just evaluate the function and all of its derivatives. At 0, what's tangent of 0? 0. Tan of 0 is 0. Secant squared of 0?
Is that undefined? No.
Nope.
No.
Secant is 1 over cosine. Cosine of 0 is
1.
1. Cosine of 0 is 1, so secant of 0 is 1, and if we square that. Now we get back down to this thing, which also has a tangent multiplication, so this value is going to be 0. And then we get down here, and this term over here that has the multiplication by tangent, that's also 0. Over here we have secant to the 4th of 0. Secant of 0 is 1. 1 to the 4th is 1. 1 times 2 is 2. So we get that as our set of coefficients. Now we can build our Taylor polynomial. So they're asking for the third order, so we're going to label it p sub 3 of x. So that means the third order. So we start with the constant of 0, and I'll just put it in just as, so we can kind of see the pattern. So it's 0 plus 1, don't need to write the 1, multiplied by x minus the center. Well, the center is also 0, so it's just going to be, maybe I'll put the 1 just so that we can really see the pattern, and I'll put the -0 just to emphasize. So that is the first order term. This right here is p sub 1. Right? P sub 1 is the first order. That would be p sub 1. That's the tangent line. Now we go to the next constant. Oh gosh, that's also 0. So that, if we did write it out completely, it would be 0 times x minus 0 to the 2 divided by 2 factorial. So what we see is that p sub 2 and p sub 1 are actually the same, right? Because this term is really just 0. So those are the same. And then we get to the term we've all been waiting for, our last term. We start with the 2. We're going to have an x minus 0 cubed divided by 3 factorial. So there is our third order Taylor polynomial. In this case, it makes sense to simplify it. We have to evaluate it at that center point, or at that approximation point. So let's simplify this one down. So p sub 3 of x, when we simplify it, that's 0. This is really just x. That's 0. This is really just 1/3, canceling a 2. And then we have our power of x, which is x cubed. So this is our third order Taylor polynomial. So that's the best cubic approximation to the tangent function near 0. So now it says we want to approximate this. And here's where we have to be careful. We have to decide what is x. So here we have p3 of x, so whatever goes in here so this is approximating tangent of x. So this is playing the role of x. That's what we're going to plug in here to get our approximation. So p sub 3 of negative 1/10. So we're just going to plug that in here and simplify it. So whatever that turns into. So we're going to have negative 1/10 plus 1/3 times negative 1/10 cubed. So negative 1/10 cubed. And if we can simplify this, we will. So that's going to be negative 1 over 3,000. And if we got a common denominator, multiply this thing by 300 over 300, we're going to get minus 301 over 3,000. If I did the arithmetic correctly.
That's what I got.
And if you type that into your calculator, what do you get to, say, 4 decimal places? Negative what?
0.100.
What about 4th decimal?
Oh, 4, sorry. 0.1003.
So that is our approximation, and if we can actually type this into the calculator, right? We can type in tangent of negative 1/10, and it's going to be pretty darn close. So that is our process. So repeated derivatives until you get to the power that you want. But again, remember that this p sub 3 is the 3rd order, so we go out to power 3. We're not counting the number of terms. The number of terms is usually 1 bigger than that. But as we see with the simplification here, we end up with only 2 terms because there's some 0 coefficients. Let's try one more here. So we're going to start with the function, natural log of x. And we need to take a sequence of derivatives until we get to the 3rd derivative because we're looking for the 3rd order Taylor polynomial. So this is minus x to the minus 2. This is going to be chain rule again, so that's going to be 2x to the minus 3. So those are our 3 derivatives. We have to choose the center, and again, we're trying to pick something that's near that number that we're approximating at, where we know the value of natural log and its derivatives. Because we're going to need to plug. Whatever we pick for our center has to be plugged in down here. So we want to pick a center that's close to 1.05 for which we know the values. Now natural log, there's only one value that we really know well, and that's natural log of 1. That's 0. Of course, we know natural log of e also. So that would be our next value that we could pick. So 1.05 is, say, right there. So we're going to surround it by values that we know and then pick the one that's closest to it. So we are going to choose 1 as our center. So that's going to be the center. So then we're going to evaluate the function and its derivatives at that center. So we're going to have y of 1, y prime of 1, y double prime of 1, and y triple prime of 1. So y of 1, of course, is 0, natural log of 1. And then here we're going to get 1, negative 1, and 2. Plugging in 1 for all of those x's. That allows us to build p sub 3 of x. Starting with the constant, we plug in a 0. We'll write out just to make sure we see all the structures. So 0 plus 1 times x minus the center to the 1 minus 1 times x minus 1 to the 2 divided by 2 factorial plus 2 divided by 3 factorial times x minus 1 cubed. So that will be our piece of 3. Because we're plugging in an x value, let's go ahead and simplify this. So that part's x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. Now we have to plug in the right x. So we have to identify x. We're trying to approximate natural log of 1.05 and natural log of 1.05, so that means that 1.05 is playing the role of x. So we're going to plug in 1.05 across the board here, so p sub 3 of 1.05. 1.05 minus 1 is 0.05. So that'll be our approximation, and we'll just need to type that in to some sort of thing, some sort of scientific-y calculator thing. So 0.05 minus 0.5 times 0.05 squared. Plus 1/3 0.05 cubed. So there is the approximation, and the actual value is, or the I say the actual value, but of course this is just an approximation also. I plugged in something wrong. Oh, 1.05. So there we have it. So we see our approximation is pretty darn close. So there's the quote-unquote actual value, and our approximation is accurate to, let's see, so 8, 7, 9. So we're accurate to 5 decimal places, and we only went out to the third order approximation. All right, any questions on building Taylor polynomials? Makes sense? Okay, let's take a look at the remainder. So just like in chapter 10, where we had a convergent series, we defined a partial sum and we defined a remainder. Same idea here. P sub n is the partial sum. It's the Taylor polynomial. And if it converges, we're going to say that it converges to the function f. So if we start, like in the last two that we did, we started with a function called tangent and a function called natural log. Those polynomials are approximating that function. There's a little bit of advanced calculus going on, just because we have built this polynomial that we can see visually by looking at graphs. This one approximates natural log of x close to 0, close to 1. This one approximates tangent close to 0. There is no guarantee that we've talked about that if you go out to infinity that you're actually going to equal the function. Okay, so as we look at taking more and more derivatives, it's approximating the function on a wider and wider interval, but there's no guarantee, we haven't proved at this moment that if you went on forever that it would exactly equal the function. That's something you do in an advanced calculus class. You prove that your Taylor series, so your Taylor polynomial going on forever, which is an example of a power series, you show that the function you started with, when you do this infinite collection of derivatives and add them together with this pattern, that infinite polynomial actually equals your original function. We haven't sort of tied the bow on that, and that you don't do until advanced calculus, where you show that your Taylor series will actually equal the function that you built it from. Because we're constructing this Taylor polynomial, which leads to the Taylor series. We're constructing it. And in the construction process, we've seen that it's a better and better approximation, but we have not proved that the function you start with, when you build the Taylor series, actually equals the original function. Like literally equal, not approximately, it's equal. So that is something that you'll do in advanced calc. But here we're just assuming that, okay, well, the function that we start with, we build this Taylor polynomial, and we can think of the function, just like we did in the last chapter, we can think of the function equal to its Taylor polynomial plus some remainder, which is a function. So we're doing the same thing that we did with chapter 10, it's just that we're dealing with a function. So the question is, how good of an approximation is your Taylor polynomial? So we want to get a gauge on this remainder. In the last chapter, the only one that we really looked at carefully was the alternating series remainder. And here is part of the reason. When you have a general function, you build its Taylor polynomial, here is what the remainder looks like. The remainder looks just like the first unused term, like in the alternating series. So p sub n goes out to the nth derivative. To get to the value of the remainder, you go one more term. You go to the n plus first derivative. So n plus first derivative divided by n plus 1 factorial, and then an n plus 1. And then it's x minus the center here. What is the one thing that is different in this term than in the nth term?
Multiplication of the constant instead of
This right here? That is the one thing that's different, right? In the two examples we just did, we plugged in what value into the derivatives? We plugged in the center, right? We did our derivatives, and then we evaluated them at the center. The center is A. This is evaluated at a random, not at a random. C is a number between x and a. It's not random, but it's in there. It's a number between x and a. You will never be able to find C. C is a mystery number between x and a. And this is why we only focus on the alternating series, because with the alternating series, we can just look at the absolute value of the first unused term. We can never find this C value, so this becomes very complicated to figure out what this is. What you can do is set up a range. You can say, okay, well, what is this expression evaluated at x? What is this expression evaluated at a? And that will tell us that the remainder has to be somewhere in between. So this remainder evaluated, I don't want to say r sub, I can't really write it because I can't say r sub n, I can say this quantity where you plug in an x, this quantity where you plug in an a, you could figure out two bounds. You can figure out a lower value and an upper value, and C is going to give you something in between. So you can get a gauge on the remainder. Kind of like with the alternating series thing, that first unused term gives us a gauge on the remainder. It doesn't tell us exactly what the remainder is, but it gives us a gauge. So that's going to be the idea here, is that we could plug in these two values and and sort of figure out a range or an upper bound on the remainder. So they do a little bit of math here. The estimate for the remainder, this number m, is going to be the maximum value when you're looking on this interval. So you've got your x value, you've got your a value, and there's going to be, you're imagining a function in there, and you're picking m to be the maximum. It is the bound on that function. And your remainder will be less than or equal to that. So where m, so you're taking this function right here, this n plus first derivative, and you're evaluating it on an interval, and that's just going to be the upper bound, the least upper bound for that function. So, super complicated. You'll do that a lot in more advanced classes, but that's the idea. In this class, we're only focusing on the alternating series to be real specific with the remainder. But the concept is similar. Concept, very similar. First unused term. Okay, so what we're going to do now is look at some very specific power series. And remember that a power series is just a never-ending polynomial. So anything of the form constant plus constant times x plus constant times x squared plus constant times x cubed, that's a power series. Not all power series are Taylor series. So a Taylor series is something we construct. You take a function, you take repeated derivatives, and you build that Taylor series. Right? You use the coefficient formula that we just did, and you build a Taylor series. A power series is more general. A Taylor series, every Taylor series is a power series, but not every power series is a Taylor series. A Taylor series is a power series because you go all the way through. Constant x, x squared, x cubed, all the way down. But a power series in general just has random coefficients like an irrational number. A Taylor series has very deliberate coefficients, like a rational number, right? You take the derivative, you evaluate it at the center, you build those coefficients in a very systematic way. So a Taylor series is very precise, very nice. A general power series is random coefficients. So every Taylor series is a power series, but not every power series is a Taylor series. And so a Taylor series is specific to a function that you repeatedly differentiate and evaluate at the center. General power series, who knows where the coefficients come from. So we're more interested in Taylor series in this class. So the first thing we're going to do is change our perspective on this statement right here. So we did this in chapter 10. We started with this infinite series right there, and we found the sum of that infinite series to be this. In this unit, or in this chapter, we're going to change our perspective. We're going to say, hey, okay, we've got these two things equal to each other. Let's imagine this as our starting function. Let's write it as a function, 1 over 1 minus x. That's a function. This is a shifted hyperbola, right? 1 over x, you multiply by -1, then you add a 1 in the denominator. This is a shifted hyperbola. That's a function. Now we've written it as equal to, this is now a power series. So this is a power series. For the function 1 over 1 minus x. That's power series. Now the obvious question should be, are you saying that if we take this function f of x equals 1 over 1 minus x, and we use our Taylor series construction process, derivative evaluated center, second derivative evaluated center, third derivative evaluated, right? If we do what we just did for natural log and tangent on the last, right at the end of the last section, will it build this? And the answer is yes. So if you have a power series equal to a function, it will be the Taylor series. There cannot be a Taylor series that you get by taking the derivatives and evaluating at the center, and then another power series with totally different coefficients that equals the same function. So if you have two infinite polynomials that equal a function, the same function, those infinite polynomials must be the same. That's what this is saying. Okay? So there are more than one ways to build a Taylor series. Typically, when we build a Taylor series, we're doing all these derivatives, but it's going to turn out that if we can find a power series for a function, it will be the same as the Taylor series. And you can verify this. You could take the first derivative, take the second derivative, take the third derivative, plug in the center, and what is the center here? Do you see an x minus anything?
0.
0, right? It would have to be an x minus 1 if the center was 1 in all these x positions. X minus 2 if the center was 0. So the center here is 0. So if you take a sequence of derivatives here and plug in 0 repeatedly, you will get that polynomial. So this power series is a Taylor series for that function. You can verify that if you want. Now, one thing that we haven't talked about yet is this. We haven't shown how to find it. So we know that this is coming from up here from a geometric series, so we know that this is true. We've already done that with geometric series. We showed that it converges from -1 to 1. It's a little different here because now we're thinking of this more like a domain. We're saying if you plug in an x value between -1 and 1, this infinite series will equal that function. But you think of it more like a domain. You're thinking what x values cause this infinite series to converge. And those are the x values that cause it to converge. We call it the interval of convergence. And we'll have to figure out how to find that. Okay, so if we have a power series, which will include our subset called Taylor series we construct from a function. So if we have a general power series, so C sub k is just random the random coefficients, x minus a to the k. So there's a random power series. Does not necessarily need to be a Taylor series, just a random power series. The following will be true. There will be an interval of convergence symmetric around its center, which is not obvious and kind of inexplicable. Takes a lot of advanced calculus to really understand this, that we have in this interval convergence at every one of those points and divergence elsewhere. Divergence out here, divergence out on both sides, and convergence in there. So clean. You cannot have convergence in random places. The convergence always will be symmetric around the center. We are going to call this distance right here the radius of convergence. The radius of convergence is this distance right there. That'll be called the radius of convergence. The endpoints are a little fishy. Endpoints have to be tested separately. Sometimes there's convergence at the endpoint, sometimes there's not, sometimes there's convergence at one and not the other. So endpoints are separate. But we have this nice clean divergence out there, convergence in here, and then we have to test the two endpoints. What image comes to mind when you see this? Have you ever talked about the radius of an interval before? No. Radius of an interval? What do you think of when you hear the word radius? Circle. It turns out that if you look inside the complex plane, so the complex, can't get that totally straight. Complex plane, so if we go to the complex plane, which we usually denote with a C with a bar, so the real numbers are down here on the x-axis, and the imaginary numbers are up here on the y-axis. It turns out that for your power series, if you change this x to a z to represent a complex number, any number inside this disk will give you convergence. Any number outside that disk will give you divergence. And numbers along the boundary here, who knows? Some could converge, some could diverge, whatever. So we call it the radius of convergence because here is what we are looking at in this class. We're only looking at that little interval right there from, to the left, whatever A is. So to the left of A and to the right of A. Totally crazy that you could be plugging in all these complex numbers that are within that disk, and you're going to get convergence for all the numbers within the disk and divergence for all numbers outside the disk. But that's why they call it a radius of convergence. And it's interesting, when you go into a complex analysis class or a complex numbers class, functions that allow complex domain values actually behave much more nicely than the real number functions. Real number functions, you can build madness. You can build functions that are continuous on the real line, but nowhere differentiable. You can build little sawtooth functions that do totally weird, crazy things, which is interesting, but a pain in the neck, that you can build these totally weird functions. In the complex plane, you cannot do that. In the complex plane, things are much more measured, much more predictable. Real functions are not predictable. So, we've got our power series, general power series. Here is the conclusion of the interval of convergence and the radius of convergence. We have three choices. Perhaps we have this case where the radius of convergence we say is infinite. That means that any x on the x interval, if you plug it into the power series, you'll get convergence. So one of the examples that we saw that this is true for is e to the x. If you look at the power series for e to the x, or the Taylor series for e to the x, they're the same. It will converge at every single number on the real line. So we say the radius is infinite, and this is going to be the interval of convergence. The case that's a little more complicated is that you can have a radius that's greater than 0, and then you're going to have the case that we just talked about, where you have convergence when you're less than r, and you have divergence when you're greater than r. This is the case where we then have to test our endpoints. So we go to our center. Radius of convergence goes both ways. We have convergence here to here, but we have to test those two endpoints and see what happens at the endpoints. In the case that is so boring, but is important to understand, it's possible that the series only converges at its center. Is it obvious that every power series converges at its center? Is that obvious? When you look at this, you told me the center was 0. Does this converge at 0? Yes. If you plug in the center, doesn't the tail become 0? Any power series will have a tail that becomes 0 at its center, because the center is always A. And if you have an x minus A, you get A minus A, which is 0. The only term for a power series that remains is the constant. When you plug in its center, the only thing that's left is whatever the constant is. All the other terms become 0 because you're plugging in A. So every power series converges at its center. Right? When you look up here, the expansion of that power series, if you plug in an A right there, you're getting 0 for every term except when k is 0. When k is 0, there's no x minus a. Right? So it's just the constant c sub 0. So every power series converges at its center. That's the most boring situation. This is the situation that requires the most work, is when the radius is greater than 0. Then we have to test endpoints. So this just tells us the following, that let's suppose we have a power series here, and we come down and we say, let's suppose we calculate the radius of convergence to be 2, and let's suppose that the center is 4. So if the radius of convergence is 2, that means we can go 2 to the right of 4, 2 to the left of 4, so that gives us all these intervals 2 to 6. But then all these things are possible. So this one has a radius of convergence of 2, but it diverges at both endpoints. This has a radius of convergence of 2, but it diverges at one endpoint, converges at the other, vice versa there, and then here it converges at both endpoints. So those are 4 options for the interval of convergence for the same center and the same radius. There's 4 choices. We have to figure out which one's the right one. So how do we find these things, the radius and interval of convergence? Well, most of the time we are going to use the ratio test, but sometimes we'll use the root test, and we're going to find this interval of convergence. So this describes our 3 cases. We'll go through and explain why. So we'll look at an example of how to figure it out. And then this just says, if the radius of convergence is some number, we then have to test both endpoints to get to the interval of convergence. So let's try one. So here's power series. No clue whether it's a Taylor series or not. The only way it could be a Taylor series if there is a function whose derivatives would build this exact series. Good chance it is a Taylor series, but we don't know at this moment when you just look at it. Every Taylor series is a power series, but not every power series is a Taylor series. So here's what we do. We see the factorial, which is a clue to use the ratio test. So ratio test said that we were going to find R by looking at the limit of the ratio of consecutive terms. So the ratio test, we do this a sub k plus 1 absolute value over a sub k. So the convergence that we are finding is absolute convergence because of those absolute values. So that's the ratio test. Same thing we did in chapter 10. It's just that here, our a sub k plus 1 and our a sub k are actually functions. Right? There's an x in them. They're not just numbers. So this is going to be absolute value, x minus 1 to the k plus 1, over absolute value of k plus 1 factorial. Don't really need the absolute values there. We'll take them away in a moment. So there's a sub k plus 1. Divided by the absolute value of a sub k, well, that's the reciprocal then. We divide by a sub k, we multiply by its reciprocal. So we get that. And actually, in this book, they use a capital R for the radius of convergence, so let me put that as a capital R. In chapter 10, we used a little r. It was going to end up being a number. Here we have a function. They're using a capital R to distinguish. Doesn't really matter. Okay, so now we have to simplify. So we end up with lim of, let's do the x's first. I see that we have 1 x minus 1 in the numerator in absolute value. Does everyone agree? We have k plus 1, x minus 1's up top. We have k, x minus 1's down below. So that leaves us with 1, x minus 1 up above. Odd power means we need the absolute value sign. Because x is could be any real number. So we can't have negatives. So we need the absolute values. And then how did the k factorial and the k plus 1 factorial, what does that all reduce to? Just k plus 1, because k plus 1 factorial is k plus 1 times k factorial, so this reduces to that. All right. Now this limit is as k goes to infinity. Is there a k in the numerator? No k in the numerator. So this numerator is constant with respect to k. So in other words, it can be factored to the front. Right, the x, there's no k in there. X is a real number. So that is constant with respect to k. Doesn't depend on k, so it can factor out. So we can think of it as acting like a constant. And what is the limit of 1 divided by k plus 1 as k goes to infinity?
0.
0. And what is 0 times x minus 1 in absolute value? 0. 0 times anything is 0. So now we're in the ratio test. Ratio test has the same conclusion as the geometric series. We have to compare this to 1. This is obviously less than 1, so what is our conclusion? Convergence, right? Geometric series less than 1 is convergence. So what this tells us, this is super important right here, that this is true for every x. This is true for all x. So if x is 100 or 1,000,000 or 10 bazillion or negative 100 or whatever, e, negative e, right? This is always 0. Does not matter what x you plug in there. You pick an x and you put it in there. You subtract 1, you multiply by 0, you get 0. So in other words, this r right here, we are getting this statement to be true for every single x. So this tells us, and I actually want to change one thing I wrote over here. I don't want to call this r. R is the radius of convergence. This is not the radius of convergence. I do want to call this just a regular r. Like the geometric series, little r, we get down, and if little r is less than 1, then we have convergence. And that's what I want there. I want the little r. This gives us convergence. This informs the radius of convergence. But it's not actually equal to the radius of convergence. What is the radius of convergence? If this is true for every single x we have less than 1, then the radius of convergence would be?
0 to infinity.
So the radius of convergence will be infinity, because we always have convergence. And the interval of convergence, when we write the interval of convergence, we're going to write it like that. So this is the simplest case. We don't have any endpoints. But it's really vital, this spot right here, super vital, to understand that. Remember that the geometric series, we have convergence whenever the little r is less than 1, we have convergence. And this is going to be 0 no matter what x you plug in. So the whole entire real line, pick all those x's, you're going to get 0, which is less than 1. Therefore, the radius of convergence has to be infinite. In other words, every single x on the real line will generate a convergent value here. Okay. Now, again, this may or may not be a Taylor series. There may be a function that when you take its sequence of derivatives, you could build this. We don't know that at this moment. All right, let's look at this next one. Again, we see a factorial, and as soon as we see a factorial, we definitely know that we want to use a ratio test. It's only going to be a very particular power series for which we would use the root test. So, little r for ratio test. It's the limit as k goes to infinity. Absolute a sub k plus 1, absolute a sub k. So ratio of consecutive terms this will be limit a sub k plus 1. We're going to replace all of the k's with k plus 1. Take the absolute value. And then we're going to divide by a sub k. So we have that. We'll simplify. Let's go ahead and deal with the factorials first. How do those two factorials simplify?
Just k plus 1.
K plus 1 up top. That is a positive number, so we don't even need absolute value bars around it. And then we look at the x factors. And with the x factors, we see that there's one extra k minus 10, x minus 10 up in the numerator. So the x's are going to simplify to just an x minus 10. But we need absolute value around there because x is just a random real number. So we want to make sure it stays non-negative. So we need that. Once again, there is no k in this x minus 10 piece. So we can think of it as acting like a constant in this limit expression. So we have the limit as k goes to infinity of the k plus 1 multiplied by this quantity x minus 10 in absolute value. And what is this limit? Infinity. This will be infinity. So that's infinity for, bless you. So that's going to be infinity. So what is our radius of convergence? So we ask ourselves, whenever we get our value for a ratio test, we say, well, when is it less than 1? Is this less than 1? No. So the radius of convergence is 0, right? There's no x value other than the center for which we will have convergence. There's always convergence at the center. And if we were to expand this out, when we plug in 0 here, when we plug in 0, we get 0 factorial, which is 1. But over here, x minus 10 to the 0 is 1. So the very first term is that. The second term, when k is 1, will be 1 factorial, which is 1, times x minus 10 to the 1, plus etc. So all of the terms except the very first term will be 0 at the center if you plug in 10. So this tells us now that the radius of convergence is 0. The interval of convergence is degenerate. It's only containing the singleton, which is the center of the series. So it's a degenerate interval. Every power series converges at its center because the tail becomes 0 at the center when you plug in the center for the x. So that's the most useless type of power series, when it only converges at its center. It's the most useless. So radius of convergence is 0. So we have to be very careful. This is one of those things it's easy to get tangled up in. So when the limit is infinity, the radius is 0. Because the r value has to be under 1 for convergence. That is never under 1. So that means the radius is 0. Here, we got the r value, the limit of the ratio of consecutive terms, to be 0. That's always less than 1, so the radius is infinite. So if we get little r to be 0, big R is infinite. If we get little r to be infinite, big R is 0. So we've got that reciprocal relationship. So these are the two extreme cases. The case where the radius is everything or the radius is nothing. So now the in-between case, the case that we will spend most of our time looking at, the part that's the most difficult to analyze. So we see this We don't see any factorials, so we could use the root test here. So the root test they used, instead of a little r, they used a rho instead of little r. They used little r for ratio test, rho for this. So let's go ahead and just stick with that terminology. So this is as k goes to infinity. And it's the limit of the kth root of the absolute value of a sub k. I said absolute value, but then I didn't write it. There we go. So the absolute value of the a sub k just cleans out that switch. So that switch just goes bye-bye. So we're going to take the kth root of the absolute value of the inside here. So the switch definitely goes away, correct? And if we take absolute value, the minus 1 of the k just vanishes. We still need the absolute value on the x, though, because the x cannot be negative. So we have that. So absolute value of a sub k takes away the switch, but we still need the absolute value on the x, because that could be negative. It's just a real number. And that simplifies tremendously. Kth root, we're going to end up with this. So we have this limit as k goes to infinity. Are there any k's left?
No.
No k. So what is the limit of that?
Absolute value.
It's going to be itself, right? Limit of a constant is itself. Because there's no k in here, this acts like a constant with respect to k. So the limit of this, now if we do what we did in the last one, you could, if you wanted to be super OCD about this, you could say, oh, well, that doesn't have a k, let's factor it out. And then when you factor this out, you'd be left with a 1 in there, and the limit of a constant is itself. So we would end up with absolute x over 5 times 1, which is absolute x over 5. But you can, of course, just jump from here to here. There's no k, which means the limit as k goes to infinity is whatever that quantity is on the inside. That quantity is constant with respect to k. Okay, so now we've done our rho, just like the little r, geometric series. We want to know when is this less than 1? For convergence, we always need to know when is this less than 1. And now we see this case that is more nuanced. You can pick some x values for which that's not less than 1. If I pick x equals 10, right? 10 divided by 5 is 2. Okay, that means we have divergence at 10. But you can also see, oh, if we pick x equal to 1, 1/5 is less than 1, so we have convergence at 1. So this gives us a gauge on the x's that give convergence and the x's that give divergence. So we multiply both sides by 5. We have that. This tells us what the radius of convergence is. As soon as we get the absolute value of x isolated, the radius of convergence is whatever's on the right-hand side there. Now, we don't know the interval of convergence yet. The interval of convergence, what we know are the goalposts. All right, we don't know what happens at the endpoints yet. So at this stage, we have the goalposts, the left and right endpoints for the interval of convergence. Because we know that this thing right here, this means -5 is less than x is less than 5. That gives us our goalposts, our left and right endpoints, but it doesn't give us what happens at those endpoints. So this is the complex part. Now we have to test those endpoints. So anytime you have the radius of convergence not 0 or infinity, you have to do the next step. So now we're going to test the endpoint. So we're going to test x equals -5, and we're going to test x equals +5. So for we know that there is convergence for all the x's in between and divergence for all the x's outside, but the two endpoints are up for grabs. We've got to figure it out. So we come back to our original series, and we're going to plug in and so here's where chapter 10 comes in. So we have the series starts at 0. It's going to be -1 to the k. And now we have to plug in -5 and figure out using our chapter 10 practice. Do we have convergence or divergence? Now we have a series of numbers. It's no longer a series of x's anymore. It's no longer a power series. Now it's just a numeric series. So we're back to chapter 10 now. All right, let's simplify this and see where we go. So we have this series, starts at 0, -1 to the k. In here, I'm going to peel out the negative sign. So that's going to be a -1 to the k multiplied by a 5 to the k, laws of exponents, divided by 5 to the k. Five to the k over 5 to the k? 1. So those guys cancel each other out. -1 to the k times -1 to the k is -1 to the...
K squared.
Nope.
K plus 2.
K plus 1.
K plus k,
2K?
2k. Right? If we have powers with the same base, we add the exponents, so we'll get a k plus k, which is 2k. So this will be -1 to the 2k. And how does -1 to the 2k simplify? 1, right? You could, let's write some gory details down here. You could write this as -1 to the 2 all to the k, starting at 0, which gives us 1 to the k, and 1 to the k is 1, so we have that. And does that series converge or diverge? What does that series do? Converge or diverge?
Converge.
So let's think about it in our minds, the expanded form of that series. What is the value, what is a sub 0? So remember, every series of numbers expands into an a sub. We're starting at 0, so a sub 0 plus a sub 1 plus a sub 2 plus a sub 3. What's a sub 0? What's a sub 1? What's a sub 2? What's a sub 3? What's a sub 4? What's a sub 5? How many ones do we have? A boatload. So this diverges by what test? Our very first test, if a sub k doesn't go to 0, then the series has to diverge. So that's for the egregious cases. Like we have the ambiguous cases like the harmonic series, 1 plus a half plus a third. Those terms are going to 0, but it still diverges. This is one of those egregiously bad series. The terms aren't even going to 0. You're adding 1 to itself repeatedly forever. So this diverges by the divergence test. So that now tells us that when we plug in -5, we have divergence. So on this side, we have a parenthesis. And then we do the same thing for +5. So we come back over here. We have -1 to the k. Original series, we're just plugging in a +5 up there. So we have -1, we have 5 to the k over 5 to the k. Well, 5 to the k over 5 to the k, those cancel. It starts at 0 also. So this all turns into just -1 to the k. So think in your mind what the expanded series is. Sometimes these ones that look so simple, they are simple, but it can be a little confusing because you don't think about the expanded series. You see just this number there. Just remember that summation of a number means you're adding that number to itself repeatedly. So here, think about the expanded series. What does this expanded series look like? What is a sub 0? What is a sub 1? Yeah, so here is the expanded series. Does that converge or diverge? Converge?
One minus one plus one minus one.
You think that converges? To what?
Zero. It oscillates, doesn't it?
So you're saying that it's getting infinitely close to the single number 0?
No.
No,
Oscillates.
right? The partial sums are going to bounce around. The first partial sum is 1. The second partial sum is 0. The third partial sum is 1. The fourth partial sum is 0. So the only way an infinite series converges is if the partial sums converge to a single number. And so because the partial sums are going to wobble around between 0 and 1 all the way down, we'll say the limit doesn't exist because there's not a single number that this series is getting closer and closer and closer to. Right? All the partial sums are just going between 0 and 1, 0 and 1, 0 and 1. They're not getting closer to a single number. So this is going to, and you can also think of it, are the terms going to 0?
No.
Right, when we look at the terms, there's a 1, there's a minus 1, there's a 1, there's a minus 1. The limit of a sub k has to be 0 by the divergence test. If the limit of a sub k is not 0, then it automatically diverges. So that's the easiest way to say this. So this is going to diverge by divergence test because the limit of a sub k is not 0. The only way we get convergence, the only way we have a chance for convergence is if the limit of a sub k is 0. If the limit of a sub k is not 0, then we can conclude really right away that there's divergence. Now we've finished the puzzle. We've tested both endpoints. We have divergence at both endpoints. So this is our conclusion right here. Radius of convergence is 5, and the interval of convergence is -5 to 5, diverging at the endpoints. So that is our interval of convergence. All right, let's stop there. Take 10. Let some of this stuff sink in. Think about questions you might have. This stuff, power series. So we've got that one. We could use the root test or the ratio test here. Either one will probably work out fine here. Does anyone have a preference or want to see one versus the other? When you think about the kth root of the square root, that's going to take a little bit of algebra. Maybe we should do that just as practice. So the root test says rho is equal to the limit as k goes to infinity of the absolute value of a sub k plus 1 divided by the absolute, root test. That's not what the root test says. So we want to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So when we look at that, the first thing we notice is that the absolute value of the a sub k is going to wipe out the switch. Right? That -1 to the k is going to vanish instantly because we're taking absolute value. So that we know for sure. And we also know for sure that we're going to need to keep the absolute value on the x part of it because that could be negative. So we're going to have that. All right, so the kth root of the numerator is obvious. That's going to be just absolute x. How about the denominator? K to the, any ideas? So we have k to the, if you think about it piece by piece, the denominator is k to the half.
It's another 1 portion.
And then we're taking the kth root of all that.
1, 2, k to the 1 over 2k.
K to the 1 over 2k is one way to write it. let me remind you of something with exponents. If you have 2 to the a raised to the b, you certainly could write that as 2 to the ab, which means you could write this as 2 to the ba, which means you could write this as 2 to the b to the a. So in other words, you can swap those exponents if you want. And the reason we might do that is that we already have in the bag that the limit of the kth root of k as k goes to infinity, what is that equal to? 1. So we've already shown that using the log limit process. So if we can sort of switch those so that we have a k through to k, that's going to help us. So we can come over here, and also, the absolute value of x, is there a k in there?
No.
No. So we can pop that to the front. So then we're going to have 1 over, and we can swap these exponents. So we have the kth root of k to the 1/2. So the denominator has a square root of the kth root of k. And that limit, remember one of the superpowers for the limit is that it can move through continuous functions. The square root function is continuous. So we can imagine this limit drilling through the square root and coming into here. And the limit of the kth root of k is 1, and 1 to the 1/2 is 1, and 1 divided by 1 is 1. So this will all be absolute x times 1, which of course is just absolute value of x. Ratio test, root test, geometric series, we always compare to 1. So we have to say to ourselves, when is this less than 1? That will tell us which x's generate convergent series and which x's generate divergent series. So if we look at that, that's pretty simple. There's no constants to deal with. So if we plug in an x equals 2 up here, we are going to get divergence. If we plug in an x equals 1/2, we will get convergence. Okay, so this tells us then that the radius of convergence is 1. As soon as we have this absolute value of x isolated on the left side of this inequality, the radius of convergence is on the other side. In your mind, you can think this, right? This is a compound inequality, correct? That's what that means, compound inequality. So radius will be 1, center is 0. Make note of that. Make sure it's clear in your mind, right? The center here is 0 because there's not x minus anything. Similarly up here, center is 0. Okay, so we now know the goalposts. We now know that we are dealing with an interval of convergence that is going to have this left endpoint and that right endpoint. But once again, we need to test those endpoints. We know that x less than 1 in magnitude gives us convergence, but we don't know about x equals 1 in magnitude. So we test our endpoints. So we're going to come over here. We go back to the original series and just plug in those numbers. So we're going to plug in x equals -1. So we come up here. Series starts at 0. We'll use shorthand notation. Just put a 0 there. We know it means k equals 0 to infinity. This will be a -1 to the k times, we're plugging in -1, so we're going to have -1 to the k in the numerator. And then down here we have square root of k. So we need to know if this converges or diverges. Now we have a series of numbers. We're back in chapter 10. -1 to the k times -1 to the k. What do those two multiply to?
1.
1. -1 to the k times -1 to the k is -1 to the 2k. -1 to the 2k is -1 to the 2, which is 1, raised to the k, which is 1. So we just went through all the details of that a minute ago, so we don't need to do it again. So that's 1 over square root of k. Converge or diverge?
Converge.
False.
Diverge.
Yes. Great. Why would it diverge? It doesn't go to zero fast enough. But why doesn't it go to zero fast enough?
P is less than
P is it's a P series and P is less than 1. So how do you demonstrate this? Arrow, you put P equals 1/2. I now know you know it's a P series. And with a P series, P less than 1 means divergence. All right, P less than 1 means divergence. All right, now we're going to test the other endpoint. So we're going to come over to x equals +1. Same idea. We just go to the original series, plug in +1. So this is going to simplify to -1 to the k multiplied by 1 over square root of k. And what kind of series is this? Alternating. And we don't have to write, so normally we would jump right into the alternating series test, but in the context here where we're just analyzing an endpoint, you don't need to fiddle with all the details. Remember that the gist of the alternating series test is if it's alternating and the magnitude of the terms are going to 0, you have convergence. That's the gist of the alternating series test. Does 1 over square root of k go to 0 as k goes to infinity? Yes. Is this alternating? Yes. So this tells us that we have convergence by alternating series test. So you don't have to do the formal limit of base of k is 0 and the sequence is decreasing. You don't have to do that. That is sufficient. But I need you to point out that you know that it's an alternating series. And so you either would say converge or diverge by alternating series test. So that tells us, let's see, on the endpoint of -1, we had divergence. And the endpoint of +1, we had convergence. So that is our conclusion then. Radius of convergence and interval of convergence. Make sense? Any piece there you want to ask about? That all clear? -1 to the k times -1 to the k is 1. All right. Okay. Time to up the ante a little bit. First one is easy. If you take two power series that converge, so this setup is that we've got one that converges to the function f, one that converges to the function g. If we add them together, we will still have convergence, and the convergence will be to either f plus g or f minus g on the interval of convergence. Okay? So that's a simple one. That's just like the derivative thing. Derivative of a sum is the sum of derivatives. Integral of a sum is the sum of integrals. So that kind of standard thing. This is the weird. This one's a little weirder. So we have our power series that converges to f. And then we multiply by a power x to the m. The new series is going to converge to the function f multiplied by the power x to the m. That part seems okay. We've got this series that converges to f. If we multiply by x to the m, the new convergent series will converge to the original times x to the m. Like, that seems very intuitive, that if you just multiply by the power. But then they have this weird little caveat here. They say when x is 0, the series converges to the limit here. I have seen no example in the book that ever uses that. I've taught this class out of like 6 different books and have never seen this actually come into play. So as far as we're concerned, you can kind of just ignore that sentence. The gist of it is this. Inside here, we've got this x to the k right there. We don't see that it starts at 0. It is possible, and we've seen a series today that had powers of x that were missing. Right, we had that tangent one where there are some powers that were 0. It is possible that this series starts with an x to the 2. All right? It's possible that you're multiplying by 1 over x. If you multiply by 1 over x, and of course if you have x to the 2 and you multiply by 1 over x, you end up with x squared over x, which is x. But you had a division by x out in front. And a division by x, if x is 0, of course, is undefined. So that's what that little caveat is like for an oddball series that doesn't start with a constant. Now, if your series started with a constant, let's suppose we just have something simple like this. So the series starts with a constant. If you multiply this by 1 over x, do you get a power series? If you multiply by 1 over x, don't you get this? Isn't that what you would get? Is that a power series? No. Power series is constant plus constant times x plus constant times x squared. It's a polynomial. Polynomials don't have division by x. Right? A power series is a polynomial that never ends. Right? Polynomials, you have no division by x, ever. That's not a polynomial. That's a rational function, but not a polynomial. And if you go on in math, you will actually encounter series like this, and they're called Laurent series, but they are not a power series. A Laurent series is a more generalized power series where you can have division by powers of x, and so you can go the other direction with all these powers that are, with x's in the bottom. So in practical terms, you can just ignore this, but that's what that's saying. The highlight here, they say k plus m has to be greater than or equal to 0 because this has to be a power series, which means the powers cannot be negative. But it's possible for this k plus m to be positive and the m to be negative, which would force you to have to take a limit. But again, in practice, you're not going to see it. But that's why it's there. I've had a lot of students struggle trying to figure out what that meant, and so that is what it means. Now the third one is super cool. So the third one, we have a composition. So this is a composition. So the composite function f of h of x. So the function, we've got this function h, and we're going to plug h in for that x right there. So we're doing a composition. And the convergence is just going to be to whatever f of h plus x is, as long as h is in the interval of convergence for f. So you did something similar to this in college algebra when you were trying to find domains of inverse functions. So the idea is this. So we've got this power series that converges to f. That one converges to f. And then we're going to stick something in for the x. We're going to do a composition. Well, the power series that converges to f has an interval of convergence. So any x that's in that interval of convergence is going to cause convergence to this function f. So when you take the composite function, you stick the h in there, the h's have to give you numbers that would be in the interval of convergence for the f function, or you would have divergence. So what it's saying, and that's what this is saying, they're saying that we'll still have convergence to f of h, to the composition, as you would expect, but only for the x's for which the h gives you numbers inside the interval that works for f, the domain of f. If h gives you an output value that's not in the domain of f, you would get divergence. So it's just the x's that are in the domain of h that give you h of x's that are in the domain of f. So we'll see. It's not going to. It's going to work out in practice to not be as complicated as it sounds right this second. All right. So these are our three ways that we can essentially build new power series from other power series. The way we can algebraically generate new power series. That's what's happening here. So combining power series. We're starting with a known power series. We call this one the geometric series. It's what we used in chapter 10. We just sort of switched the sides though. So we're thinking of 1 over 1 minus x as a function, and it's equal to this power series. We call this one the geometric series. And let me point out that there are a lot of specific power series that we are going to be using in here. And it is a very good idea if you go to the handouts to start looking at this group of power series right here. So I broke them into two groups of 6. These are the most common power series that we're going to see. So these are 6 that are based on the geometric series. Actually, why don't I walk through this a little bit while I have it up here. So the geometric series is our root power series. It's our base power series for the following. So we've got this power series. Again, with a power series, it's just a polynomial. The easiest type of function to integrate and differentiate is a polynomial, power rule. To get from here to here, I just integrated. Right, if you integrate this, you get natural log of the denominator divided by the derivative of the denominator. If you integrate 1, you get x. If you integrate x, you get x squared over 2. If you integrate x squared, you get x cubed over 3. So power series, you can integrate term by term to get a new power series. Or you could differentiate term by term to get another power series. We'll deal with the intervals of convergence later, but this is how we got to this power series, integrated. To get to this power series, I replaced x with negative x. So we've got this power series here. If I turn all the x's into negative x's, boom, we get a new power series. Turns out it will have the same interval of convergence. This one is called the geometric series. I call this one the alternating geometric series, because it's alternating. So we took the geometric series and made it alternate. So we've got the GS, that's the alternating geometric series. This one is just the integral of that. Integrate 1, get x, integrate x, get x squared over 2, etc. Integral of this is just natural log. You don't need the absolute values because the interval of convergence creates a number in here that's greater than 0. If you look at both of these, you might say, oh, wait, shouldn't we have an absolute value in here? And the answer is no, you don't need it because the numbers in here don't ever create a negative in there. So you don't need it. Now this one is just a shift. Take this one and say, hey, let's replace all the x's with x minus 1. So if you turn all the x's into x minus 1, we now have a new power series. Center of this power series, though, is 1. All right, so its interval of convergence will be centered around 1. And this one, the most interesting of them all, arctan. Don't we integrate that to get to arctan? So if we integrate the left side, we get to arctan. Integrate this, we get x. Integrate this, we get, let's see. Did I say that right? No, there's one missing step. That's not, the integral, that's not arctan. What is the integral of what integrates to arctan? 1 over 1 plus
X squared.
X squared. So to get to this arctan one, first we're going to replace all these x's with x squared. So we have 1 over 1 plus x squared. And then integrate to get to this one. So these 6 are all based on the geometric series. The next 6 are all based on the exponential function. So the exponential, we've already seen this power series. We have built these two, and we saw with tangent we also had some zeros in there. So with sine and cosine, the sine is an odd function, and it only has odd powers. The cosine is an even function, it's only going to have even powers. And the piece that's super interesting, if you look at sine and sinh is just the same as sine, except it's all positive. Cosh is the same as cosine, except it's all positive. And now look at this. If you add sinh and cosh together, you get the exponential function. If you add sinh and cosh, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So e to the x can be written, and we saw this when we did the hyperbolics, that we had ways to write the hyperbolics as exponentials, and this justifies it. We see that e to the x is sinh plus cosh. And then this one is the binomial series. We'll talk about that one. That one's not really based on e to the x, but I put it with the ones that are based on e to the x. Okay, so that brings us to here. So we've got our geometric series right there, and all we're doing is multiplying by a power of x here. Okay? So the power series here is x cubed multiplied by the power series for 1 over 1 minus x. K starts at 0. So the way that this is written, it's not a power series yet. We have to do some addition. Like we have to add these exponents. There is the new power series. All we did was distribute the x to the 3 to the inside. We added them together. There's no division by 0 because x cubed doesn't have a 1 over x in it. So our interval of convergence has not changed. So let's look up here. So multiplication by a power, the series converges to x to the m f of x. For all x not equal to 0 in I, if x equals 0, then it converges to the limit. We can ignore that piece. It's just going to be x to the m times f. So the interval of convergence does not change. It's still I. So this was absolute x less than 1, so that has not changed. Nothing has changed. So there's our new power series, and it converges for all x less than 1 in magnitude. I'm not sure why I put this one down here so far. Okay, next one. So that one is a multiplication by a power. This one. The first thing we're going to do is look up here and notice that we took this x and replaced it with x cubed. So this is the third one up here. This is the composition one. So this, the power series here, we're going to take the power series for 1 over 1 minus x and just replace x with x cubed. So we are going to have this. So we'll replace x with so we come up to this power series right there, take that x, replace it with x cubed. Let's do a little simplification. So our simplification is that this power series is now x to the 3k. K starts at 0 still. Now, interval of convergence. So this piece that sounded more complicated than it is. So the original power series for the geometric series is -1 less than x less than 1. Right? That's the original. It's the same as this one right here. You can write this as a compound inequality. So all this says is that if you replace x with x cubed in the power series expression, you also replace x with x cubed in the interval of convergence expression. That's what this says. H of x is in I, so I take h of x, plug it in for the x that was in I. And then we simplify that. Okay. Compound inequality, if we take an odd root, you can just do it straight across, right? So absolute x is less than 1. So the convergence interval, the interval of convergence, didn't change. So that's a new power series. Now again, we don't know if it's a Taylor series or not. Remember that a Taylor series is constructed. You start with a function, take repeated derivatives, and build your series. This may or may not be a Taylor series. It's a power series for sure because it's an infinite polynomial, but we don't know, did this generate from, can we make this from here? We haven't proven that. Most likely, yes. If we take this and take all its derivatives, it will build the same exact series, most likely. Okay, well, let's go to this one. Okay, so now we start with this power series, which if you look at your 12 common power series, this is one of them. We're closely related. So we've got that. Then we look down here. This is just a multiplication by a positive power in x. There's no division by x, so we don't have to worry about that limit thing in that middle one. So again, this is multiplying by a power of x. So we're going to take the power series for natural log of 1 minus x, and we're going to multiply it by x squared. And the way we have this right now, this is not a power series yet. Right? This is a power series times the power of x. So we haven't written it as a power series yet. So we're going to move that x squared to the inside, and that's going to be x to the k plus 2 divided by k. There is our new power series. And when you multiply by a power of k, the interval of convergence does not change. And you can write your interval of convergence that way. If you wanted to, you could write it this way. Doesn't really matter. Either way. So when you multiply by a power of x, does not change the interval of convergence. There's no weirdness, just same interval. Okay, next one is a substitution again. Next one is a substitution. So this is going to be, we're going to take the x up here and replace it with x to the 4th. So all the x's become x to the 4th. We're replacing x with x to the 4th. So we come up there. Okay, there's a negative, and then we have our series, which starts at 1, not 0. And we're going to replace that x with x to the 4th. So we have x to the 4th to the k, all divided by k. Well, in our interval of convergence, we just do the same thing. We do that. So our power series will be x to the 4k divided by k. And now we have a little algebra dilemma. When you have an even power in a compound inequality, you cannot just take the 4th root of all sides. You can't just do that. With an odd power, you can do it straight across a compound inequality with an odd power because you can take an odd root of a negative. We can't take an even root of a negative, so we can't just willy-nilly take the 4th root of both sides. But what we can do is this. First, I'm going to give you a graphical interpretation of how you can think about this. So if you think about the function y equals x to the 4th, it's going to look something like that. So this is a picture of y equals x to the 4th. And we want to know when, we want to know for what x values is this true. So we're looking on the y-axis at 1 and negative 1. Ooh. Let's see. Undo. So we're looking at 1 and negative 1. Can I just go a little bit? Okay. So we want to know what are the x's that give us y values in here. All right. So we're looking at the x-axis. There's negative 1. There's positive 1. That, of course, corresponds there. That corresponds there. Maybe I should make those open circles, though. So, what are the x values? Oh, this one's equal to -1. Is that there's no equal to -1 down there, so that's okay. So what are the x values that satisfy this? What are the x values that put us in this yellow band? So lower than 1. We want to be lower than 1. So open parenthesis, but could possibly be equal to -1. Not that it matters here because there's no graph down there. But what are the x's that put us in that interval? -1 to 1. That is our new interval of convergence, so we would write this as open on both sides of that interval. So that's a visual way to do it. Here's another way to do it, which is not completely, here's another way I think is fine to do it. So here's a compound inequality. That corresponds to x to the 4th less than 1. Isn't it true that this is always true? X to the 4th, no matter what, it's always greater than or equal to -1, correct? Right? It's x to the 4th. It's an even power. It's always bigger than any negative. So you could say that this is true. And then you could say that let's see. Let me think for 1 second. There's you can say that that is true. And then you could do this. What do I there? There's a clever algebra way to get at this that. So if everything is non-negative, you can take the square root of both sides. If everything is non-negative. So like if you have something like this, 0.1 is less than 2, that's true. It's also true then that the square root of that is going to be less than the square root of that. So if things are all positive, if you have a true inequality and everything's positive, the inequality without the square roots is going to be true, as well as the inequality when you do the roots. So you can do this. This isn't the most sound algebra, but you can justify it. So then you get that. And then we're in the same case again. Okay. But again, this is always non-negative. This is always positive. So then we should be able to take the square roots again. And what is the square root of x squared?
Absolute x.
Absolute x. So this puts us here, which of course is the same as that. So that's kind of a clever, sort of technical algebra way you could do it. I think it depends on whether you're a visual or more algebraic in your mind. Like I think this makes a lot of sense visually. When you think about this as a function, think about that as a y value. You want it to be less than the y value of 1 and greater than or equal to the y value of -1. And then you're just looking at the x's that satisfy that. All these x's in here are going to satisfy that. So it's a very good visual way to think about an even power inside of an interval. But you could do this clever little thing where you take square roots as long as everything is non-negative. It will work. Okay, so let's go to the next way to build. So what we've just been doing is building new power series from existing power series. This just says, well, a power series is really a polynomial. And if you differentiate a polynomial, you get a new polynomial. If you differentiate a power series, you get a new power series. So this is just codifying that if you want to take the derivative of this power series, you'll get a new power series, bring down the k, subtract 1 from the exponent, interval of convergence will still have the same interval. Same interval, still going to be less than r. You can do the same thing with integration. You can integrate your power series by adding 1 to the exponent and dividing by the new exponent, and you still have that. Now, the one drag about derivatives and integrals of power series, the one drag is right there. The power series that gets integrated or differentiated has the same boundary points for the interval of convergence, the same goalposts, but the endpoint convergence could change. The beautiful thing about the ones we just did, where we did composition and we multiplied by powers of k, I did not change. We had no issue with the endpoints. I did not change. The interval was identical. When you're differentiating and integrating, you've got this extra piece. Like we did with the ratio and the root test, for finding the interval of convergence, we have to test the endpoints again, unfortunately. So whenever a series is differentiated or integrated, the endpoints need to be tested. Frequently, when you're differentiating a power series for a new power series, frequently you lose convergence at the endpoints. You're differentiating, things are going to 0, you sort of lose a term and you lose convergence. And frequently, when you integrate, you gain convergence. So if we go back to that handout for a second, there was an example of that right here. When we go from here to here, we integrated, and notice that we then included an extra point of convergence. If you plug in -1 right here, you get natural log of 2 minus natural log of 2, not a problem. So just be aware of that that's usually what happens. If you integrate, your chances of including an extra point of convergence are there. And if you're differentiating, you often lose one. So you can think about going this way for differentiation. If you differentiate this, you get that, and you would lose a point of convergence. So let's try it and see if we can see such things. Okay, so this topic right here will be the hardest topic on the next exam. It is the most subtle of all the topics we're going to deal with in Chapter 11. So the idea is that we have a power series that we're starting with, and we need to figure out how do we get to G from F with differentiation or integration. We need to know, how do we get to G from F? And do you think we're going to integrate F or take the derivative of F in order to get to G? So if you integrate F, what kind of function do you get right away?
Higher power.
Because that power's in the denominator, though.
Natural.
You get a natural log, right? If you integrate 1 over x, you get natural log. So if you integrate this, you get some shifted natural log business, which is not getting closer to G. So it's actually going to be a derivative process. Let's check. So if we write F in an easily differentiable way, we would write it like that. There's F. And let's notice that as we start taking derivatives, so there's the first part of the derivative, bringing the power down, subtract 1, but then we have the chain rule and we have to multiply by the derivative of the inside, so we have to multiply by a -1, which then is going to make this outside +1. When we differentiate by a -1 from the inside. Now let's go, we see, gosh, we're getting closer, right? Now we have a power of 2 on 1 minus x. So we take one more derivative. So we bring the power down, subtract 1, And then chain rule says, oh, now multiply by the derivative of the base. The derivative of the base is once again -1, so we get that. Bingo, we close. So you with me there? So you see f double prime is 2 divided by 1 minus x cubed. Everybody see that? Now, we want g, which has no 2 in the numerator. So if we divide both sides right here by 2, then we have 1 over 1 minus x quantity cubed. That's g. We now have a roadmap for g. G is the second derivative of f divided by 2. We now have a way to get to g from f. So to get the power series for g, we take f's power series, differentiate it twice, and then divide by 2. Okay, so let's do that. So g of x, whoa, not yet. So we have f prime of x. Let's do this. I'm going to start from scratch. So let's get the whole power series for f. Even though we see it up there, let's just write all the power series here so we can be more careful. Okay, so there's f. And we want to get to its second derivative. And this interval of convergence is -1 to 1. So now f prime. So we come in here, we're going to differentiate, so we bring down the power, subtract 1 from the exponent. And we have a little subtlety with the index here. We've got to be careful. Do the k values start at 0 still, or do they start at 1? So think about this. If you have a polynomial 1 plus x squared, and you take its derivative, don't you lose a term? Right? That first term drops off. If you have 1 plus x squared and differentiate, the 1 drops off. That's one way to think about, oh, we lost the term. We now need to start at 1 instead of 0. The other way that's obvious is this. If you plug in 0 for this k, you get x to the -1, which is 1 divided by x. That is not a polynomial. We cannot have 1 divided by x. That's not a term in a power series. Power series means powers of x, non-negative powers of x. So that's another way to sort of convince yourself, oh yeah, we got to start on. Another way is to differentiate up this in your mind. You're going to have 1 plus 2x plus 3x squared. So the very first term should be 1. So then we come down here. If you plug in 0, you don't get a 1. But if you plug in 1, 1 there, you get x to the 0, which is 1. So you just want to make sure that your derivative, that the index is what it's supposed to be so that the derivative matches what you get. Okay, now we take another derivative. All right, we can do that. So let's not put an index yet. So this is going to be k times k minus 1 times x to the k minus 2. All right, just bring down the power, subtract 1. Regular derivative. And then we go through the same process again. We say, okay, well, should k start at 1? Should it start at 0? Should it start somewhere else? Lots of ways to convince yourself that this needs to start at k equals 2. If you plug in k equals 1 or k equals 0, you get division by x, which is not a polynomial. So that's out. So now we've got that. And we are very close. So g of x, what we're trying to do, is the second derivative of f divided by 2. So here is the power series that's the power series for g. And the interval of convergence, we know that its goalposts are -1 to 1. We know its endpoints are -1 to 1. But anytime we differentiate or integrate a power series to get to a new power series, you've got to test the endpoints. So derivatives and integrals, we have to test the endpoints. Based on our rule of thumb that differentiating often loses convergence, that rule of thumb is going to say, we probably aren't going to gain convergence by taking derivatives. But we still have to test. You always have to test when you use a derivative or an integral. So we're going to test x equals -1. So we're coming in here to this power series. We're going to plug in -1 for x and figure out if it converges or diverges. Do we care about this 1/2 out in front? No. If we have a series that converges and you multiply it by 1/2, it still converges. And it does not change the interval of convergence. If you have a power series that diverges and you multiply by 1/2, that's not going to change anything. Now, I did say something right there that's a little bit hand-wavy. Do you see in your mind why multiplying a power series by a constant is not going to change the interval of convergence? Do you see why that might be? What test do we usually use to find the interval of convergence and the radius of convergence? The ratio test. So if you had an a sub k plus 1 over a sub k and they each had a 1/2 out in front, those divide out. So if you multiply a power series by a constant, you're not going to change the interval of convergence. Because in the ratio test, those constants would vanish. So let's just forget about the 1/2 when we go to analyze this. So this starts at 2, we have a k minus 1, and we're plugging in -1. -1 to the k minus 2. So my first question is, are we dealing with an alternating series or not? We've seen some -1s where the power on the -1 ends up being a 2, so it's not really negative. Is this truly an alternating series? Yes, right? That's an odd power, that's an odd coefficient in front of the k there. So if you think about plugging in a 2, we start out with a positive because that's a 0. So -1 to the 0 is +1. If we plug in 3, we get 3 minus 2, which is 1. -1 to the 1 is negative. So it is going to alternate. It's truly alternating. It's not, it is alternating. So alternating series test. First piece of the alternating series test is essentially the divergence test. With an alternating series, this is your a sub k. For an alternating series, we don't include the switch. Does this alternating series converge or diverge? Diverge, because the gist of the alternating series, two things. First, is it alternating? Yes. Are the terms going to 0? And the answer is no, right? Those a sub k's are not going to 0. Those are the only two things we have in our mind with the alternating series test. Okay, the limit is 0. Are the terms going to 0? No. All right? So this diverges, you could say, by the alternating series test or simply by the divergence test, because the limit of this is not 0. So easiest way is just say by the divergence test. And then we plug in the other x value, +1. Same setup, starting at 2. We've got a k, we've got a k minus 1. And now we're plugging in a 1 there, so we just get that. Does that converge or diverge? Diverge, right? The a sub k is not even going to 0, so this is an egregious divergence. This really diverges. So that diverges also by the divergence test. The limit of a sub k is not 0. So remember, this is what the divergence test means. The limit of a sub k is not 0. So therefore, our conclusion is that the interval of convergence is, I guess we want the whole thing. So here is our g of x with its interval of convergence. So we can build new power series from existing power series by taking derivatives. Okay, so look at that example super carefully. We'll start the next one and do one piece of it, but look at this carefully because this is the hardest part. This is the hardest question on the exam, is building a new power series from another power series using derivatives or integrals. So let's just do the very first piece of this. We want a power series for G from the power series for F. F is a super easy power series to generate. We'll talk about why that is in a moment. I'm more interested in this key statement right here. What is our roadmap? How do we get to G from F? So when you're looking at G, what do you think you're going to do to F to get to G? Integrate. Let's check. So if we take the integral of f of x dx, that's the integral of x over 1 plus x squared. It's log form-ish if we multiply by 2 and divide by 2 on the front. Now it's in log form, and this will be equal to 1/2 natural log. Don't need an absolute value. That denominator is always positive, plus c. So, that make sense? All right, we'll stop there. We'll pick this one up on Thursday. Maybe try to finagle it a little bit and see if you can figure out how to build G from F, because that's tricky, very tricky. Enjoy the rest of your tax day. Hopefully your tax return is going better than mine has been going. Good. I'd love to be able to e-file, but a space in the wrong place? Rejected. Silverton. Have you skied it?
No, I don't ski.
Oh, have you snowboarded it?
I don't snowboard.
You sled? Imagine going to the top of Silverton Mountain and sledding down.
You actually have to get up there by helicopter.
Yeah.
You have to take the Durango Silverton train.
Have you done that?
No, I'm from Durango.
You are?
Yeah, I've done the train. I've never done the helicopter.
Yeah, the helicopter looks so crazy. Oh, yeah. Got some friends that did that this year, and they said it was so cool.
Yeah.
And I got a couple of friends that they went before Silverton was open, because they don't open until later in December, because they don't have any, like services. And they were just hiking to the top of Silverton Mountain and then skiing and snowboarding down.
Yeah. It's a pretty big mountain.
It seems huge.
Yeah, it looks big far, and then it's really big.
Were you close?
Yeah.
Yeah, we were going to go there for spring break, but then my son had some surgery and we never got to go.
Yeah, I love it down there.
Did you mountain bike in Durango?
No, I don't really do that stuff.
That stuff? We went down, my kids were both mountain bikers, so we went to Durango to race against the Durango team
Oh, nice.
a few times.
Nice.
It was quite fun. Because there's some very good mountain bikers down there. See you guys Thursday.
Yeah, I live down there.
Yeah.
Wish I could live down there, but it's so expensive.
Yeah. And how is Fort Lewis? Did you go to Fort Lewis at all? Or?
No, we moved up here around like 3, 4.
Oh, so you've been up here for a long time now. Yeah. It's crazy how expensive the whole western slope has gotten. When I was in college, you used to be able to go out and buy something in Paonia or further south for like nothing.
Yeah.
And now it's like all expensive all the way down.
Yeah, the whole like San Juan Valley. Is
San Juan
so
Valley is,
expensive.
yeah,
Yeah. Well,
ridiculously expensive.
thanks, Professor.
Crazy. You bet.
I have a question about the test that we did for